So again, Michael Perlin, JPMorgan Chase. I want to first thank the conference organizers for inviting me to speak here. Yeah, I want to tell you a little bit about quantum error correction. So obligatory disclaimer, so opinions any I give are my own. I don't not necessarily representative of the firm, but you know, I'm still might give some opinions. I want to start by at least telling you like the goals of my talk here. I was asked to give a talk for applied mathematicians, right? So I expected I'm going to have a diverse audience from people that know a lot about quantum computing to maybe people that know nothing at all. And so my goals here to start are initially just introduce key concepts in quantum error correction and maybe equip you a little bit to, if you go out there and start reading a paper, you'll recognize some of the words, maybe know what they mean, and be able to navigate more easily. So introduce key concepts. I want to identify the primary objectives and challenges of the field. From there, I'll hopefully increasingly, as we get later in the talk, tell you more about current research topics and recent breakthroughs, and then I'll end with some both natural and speculative future directions. So a disclaimer from the get-go, I'm going to focus on sort of standard quantum error correction based on qubit systems. I'm not going to talk about bosonic error correction, measurement-based quantum computing, which has its own way of doing error correction, and measurement-free error correction. That's not because these aren't awesome and active subjects. I just sort of have to make trade-offs in time. All right, so why are we talking about quantum error correction? Well, I think it's uncontroversial here to say a lot of us want quantum computers to be around. We want to use them to solve lots of interesting problems. But why don't we have them yet? What are the obstacles? And sort of I assert there are essentially two obstacles, the biggest ones to deal with. One is current hardware capabilities. So we have physicists working very hard to make us better and better quantum computers with lower error rates. And the second is error correction overheads. It's a big theoretical bottleneck for being able to use quantum computers. So I'll talk a lot about overheads in this talk. And essentially, these overheads, this becomes a big bottleneck because errors are a fundamental problem for quantum computers in a way they are not for classical computers, although classical computers also use error correction all over the place. So for various deep reasons having to do with the fact that you can't clone arbitrary quantum data, at the end of the day, what it comes down to is when you have a quantum computer, you need to have perfect control and isolation of the quantum information. Right? So if you have a quantum bit, any interaction with its environment that was not what you intended to happen will corrupt your data, right? And start giving you just random numbers and garbage from your quantum computation. And so what that means is that the fidelity of your calculation, or some measure of how well did you compute what you meant to compute, ends up falling exponentially with the number of operations you perform on the computer. Because at every instant, there's sort of some probability of failure, and that accumulates very quickly. So what does this mean? Really, back of the envelope, say you have a quantum computer, say every operation you perform, there's something like 10 to the minus 3 probability of error, which is roughly representative of where hardware is at today. You have a budget of something like 10 to the 3 physical operations before you start just getting random bit strings from your quantum computer. So for reference, sort of, you guys might have heard about possibly, cryptography applications of quantum computing. So the state of the art for breaking some cryptographic protocols with a quantum computer today involves something like 10 to the 7 10 to the 7 gates, not physical operations, right? And so this is sort of hopeless to do with the bare hardware at 10 to the minus 3, even 10 to the minus 4 error rates, right? And in fact, the problem is so bad that there are algorithmic implications for how you might use a quantum computer, what you might be able to do with it because of error correction. So we all love exponential speedups. That's what we want. This is sort of the goal. But these turn out to be rare. They exist, but they're sort of few and far between, right? But if you get a graduate student to work on quantum algorithms, you tell them to start poking around, look at classical algorithms, see whether you can make quantum versions of them. What you'll get is quadratic speedups sort of all over the place, right? So quadratic speedups occur everywhere in quantum computing and quantum algorithms research. And by quadratic speedup, just to be precise about what I mean here, if you have a classical algorithm takes some runtime has a runtime some function of your problem size, right? The quadratic speedup means the quantum computer sort of asymptotically should have a runtime that scales with the square root of that problem size. So this is kind of like what Jeff just told you about how brute force search classically you should take order n time to find what you're looking for in a list. Quantumly you can find root n. So this is a quadratic speedup. So Google, some researchers at Google took a hard look a few years ago at what a quantum computation looks like with error correction accounted for. And their conclusion was basically that you should ignore quadratic speedups, right? When you account for the overheads of error correction, that kind of wipes out all the benefit. So their conclusion was look beyond quadratic speedups. Another possible conclusion is that, well, maybe you should come up with better error correction routines. All right, so that's a long motivation. Okay, so from here I want to introduce you to some actual key concepts of the field. I'll give you sort of a lightning crash course on the repetition code as an example, classical repetition code. So say you want to send me a message. Your message is a bit string, and some of the bits might be corrupted en route. So what do? Simplest thing, you just give me the message, multiple copies of the message. So for 0, you send me 0, 0, 0. For every 1 bit, you send me 1, 1, 1. Right? And so this is called the 3-bit repetition code. So the code refers to the set of sort of valid bit strings that you could send me, 0, 0, 0, 1, 1, 1, for every individual bit. And so in the repetition code, I can just sort of write this down. More generally, the way that we like to define error correcting codes, or linear error correcting codes, is with a parity check matrix. And the code words consist of the null space of this parity check matrix. I hope I'm not scaring, I hope this isn't too much. I do have a room of mathematicians. Hopefully, this is digestible. So for the repetition code, here's a parity check matrix I could use, for example. What does it do? The first row says that if I add the first 2 bits of a code word, I should get 0 mod 2, right? And the second row says if I add the second and third bits, I should get 0 mod 2, right? So valid code words are defined by anything where I act this parity check matrix on it and I get 0 mod 2. Everything will be mod 2. Okay, so what does this parity check matrix do? It does more than just define my code space. It also lets me diagnose errors. So if I get a word, say the first bit was flipped, so I have an error, 1, 0, 0, which says flip the first bit. You sent me a message, it's been corrupted by some errors. I act with this parity check matrix on it, I get a syndrome, right? So errors induce syndromes. And then what I do with that syndrome, I want to decode the syndrome and try to figure out what error most likely occurred so that I can correct that error and actually read the message you sent me, right? In general, this is an NP-hard problem. So error correcting codes on their own are not very useful. So when you give me an error correcting code, you also need to give me an efficient decoder so that I can actually read messages that I get. All right, the last object I want to introduce here is another way to represent classical error correcting codes, and quantum ones later on. It's called the Tanner graph of a code. And this is another way to represent the same parity check matrix that I have up there. So I have 3 data nodes at the bottom. This is where 0, 0, 0, or 1, 1, 1 live. And I have check nodes, which correspond to rows of my parity check matrix. So this first red box on the left says that the first 2 bits that it touches have to have even parity when I add them together. All right. And so part of the reason for me to show you all this is to show you, show some of the math that's involved in the theory of error correction. So you'll see lots of, Boolean linear algebra, and more generally, linear algebra over finite fields, which can get pretty fun. And then you'll see lots of also graph-based methods to do, construct codes or decode them and so on. All right, so I have a code. How do I characterize it? Universally everywhere, you will see these 3 letters that people talk about for an error correcting code, N, K, and D. This refers to the first number of data bits in the code. So the repetition code, I had 3 data bits, 0, 0, 0, 1, 1, 1. K is the number of message bits. So you sent me 1 bit with every, so there's 1 message bit for every 3 data bits. This lets me talk about the code rate already, how efficient, what's my encoding rate, what's how much did I get for every bit that I used. And the last parameter here is maybe the hardest to make sense of, but it's not too bad. It's called the code distance. So the code distance is the minimum handling distance between code words. For the repetition code 0, 0, 0, 1, 1, 1, they're 3 sort of bits apart. Equivalently, it's the minimum Hamming weight of an error that I cannot detect. So if you flip all 3 bits, I don't know what the error, I can't detect that error anymore. And so the distance tells you something about the robustness of this error correcting code to errors, right? And you can actually make that intuition more concrete. I am guaranteed to be able to correct some number of errors that's directly related to the distance. It's about half the distance, up to some fiddly business with, it's the biggest integer less than half, but it's basically half. Okay, so the repetition code as an example is an N1N code. I use N bits to, N sort of physical or data bits to encode one logical or message bit, and it has distance N. So this is a very robust code, but it's not at all efficient, right? What you want are what are called good codes. So here good, the word good is jargon, and this is where both the number of bits that I encode and the distance both grow linearly with the number of data bits that I use. All right, so in the quantum world, basically all of this, almost all of this carries over. We now put 2 brackets around NKD to denote that we're talking about a quantum code. N is now the number of physical qubits that I use. I saw a question on the board, by the way, about physical versus logical qubits. So physical qubits are like, individual hardware components that is 1 qubit. Like logical bits is how many qubits do I get that are error corrected out of all of this, right? So you still have a notion of code rate, how efficient, how many logical qubits I get per physical qubit. You can't quite define distance the same way as we did before, but you can still talk about the weight of an undetectable error. That still carries over. That still relates directly to the number of errors I can correct. And you still have a notion of good quantum error correcting codes, where the number of logical qubits you encode and the robustness of the code grow linearly with the number of qubits, physical qubits that you have. All right, so the last sort of technical background that I'm trying to expose you to hopefully make it easier to look at error correction papers if you're out there in the wild. I should talk about actual quantum codes. And the formalism people usually use, or the most common formalism out there, are what are called stabilizer codes. And the way you define a quantum code now is it's some subspace of a Hilbert space. So quantum states live in a very large vector space, right? So the code space is some subspace within that vector space, which is defined as the +1 eigenspace of a bunch of operators or matrices called stabilizers or checks. So here, my space consists of states psi, which are +1 eigenstates of a bunch of operators S, or a bunch of matrices S. All right? So I can construct operators which will exactly measure qubit parity. So if you're familiar with the Pauli matrices, some of you may or may not be, but I can construct, for instance, Pauli Z on qubits 1 and 2. The product of those 2 operators measures the parity of those 2 bits. So this is how I can sort of get the classical code as a special case. I just make these checks, the parity checks, on a bunch of qubits. But in quantum mechanics, I have to deal with more than just bit flips. I also have to correct phase flips, right? So in addition to errors that take 0 to 1 back and forth, I have phase flips that take 0 + 1 to 0 - 1. And so the thing that you'll see a lot is people often organize this into what are called CSS codes, where we have a bunch of data qubits. This is now a Tanner graph of a CSS code. We have a bunch of data qubits. We have a bunch of matrices or operators that measure sort of Z-type checks. So one of these might measure Z, 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 Z on 4 qubits, and ones that measure X-type checks, and these respectively deal with bit flip errors and phase flip errors sort of independently. And so together, then you have a quantum code that corrects any type of error. So what do I do with these operators, or stabilizers? I measure them. And that's exactly what my syndrome is. So if you remember, syndrome was the thing that sort of tells you that you can use to infer what error might have been there, right? So my syndrome is a bunch of measurement outcomes for each of these stabilizers, and that's what I then decode to infer what error occurred on my quantum computer. Okay, so there's a particular error correcting code that you've heard of already earlier today, but it's a really important one to know, and this is the surface code. So what I'm showing you here is the Tanner graph of the surface code, but it may as well just be how you lay out the qubits, right? You can print these qubits just in a grid. The data qubits are just normal qubits. Now the checks, I also assign a qubit on to each one of the squares, and I'm going to use that qubit to measure the check associated with that square. And one of the very nice things about the surface code is that it only uses nearest neighbor connectivity, right? Qubits only need to talk to their neighbors on here, which is very nice if you want to say, print, we imagine printing silicon wafers for our computers, right, in solid state. And so there, if you have a qubit that's pinned to one spot on your chip, you know, this surface code is very nice that it really only needs to talk to the other qubits nearby that are pinned down. So as an error correcting code, maybe this is a little bit too much, but it's an L squared 1L code. It turns out you can maybe print a bunch of copies of these, but what this means is that I have, say here, a 3x3 grid of data qubits. The distance turns out to be 3, so I need an errors need to go from one side of this patch all the way to the other to become a logical error. And so my robustness grows with sort of the linear size of this chip. And so this code is sort of decent in some ways. So it's fairly robust. The robustness is something like the square root of the total number of qubits that you use, which is not good in the sense of being linear with a qubit number, but you know, it's pretty decent. The real problem is that the efficiency of the surface code isn't too great. So in fact, there's a trade-off between the efficiency, how many logical qubits per physical qubit, and the robustness of the code. The more robust I make it to errors, the less efficient my code is in terms of how many logical qubits I get per physical qubit. So leaning into that a little bit, if I write this, this relationship between the logical qubit number, the distance, and the physical qubits for the surface code looks something like this. I'll remind you a good code that we want, that one might want, one could hope for. Each of k and d would independently grow linearly with n. And it turns out there's kind of no way around this trade-off if you want to print a chip and have every qubit talk to its neighbor. So there's something called the BPT bound, which says that if you have a code embedded, a quantum error correcting code embedded in 2 dimensions, where the stabilizers, the operators you want to measure, have sort of bounded support. So each one has some, you know, bounded size independent of how big my code is. So that's exactly what the situation was with the surface code, where every stabilizer was just kind of 4 operators sort of around 1 qubit. Yeah, you have to have this trade-off, right? And this has immediate implications for you know, the overheads of a quantum error correction. So as a back of the envelope, say I want to encode just 1 logical qubit. And I want to encode it with a code of distance 10, so I can correct, you know, a handful of errors, you know, 4 or 5 or something. Right away, this tells me I need 100 physical qubits. So I'm really quickly picking up orders of magnitude in terms of physical overheads for error correction. And in fact, even here, this was a little bit optimistic. So Google, who's really leaned into the surface code architecture, if you read any of their papers, they'll say that what they want, they're really targeting something like distance 30 code, which right away needs over 1,000 physical qubits per logical qubit. All right, so we're picking up more orders of magnitude as we go. So you know, you can sort of accept that and say, I'm going to run with this. This is what we're going to do. We're going to print a lot of qubits. We're going to build a massive. You know, we're used to having giant data centers for. So a quantum computer might be something like a giant data center. But there are some alternatives that you have. So one breakthrough that's happened in the last few years is sort of demonstration of architectures that involve qubit movement. So now you can have something talk to something very far away. You just physically move that qubit. So this has been done in neutral atoms and in trapped ions. And then another loophole that sort of, I think, people are only starting to realize, there's not as much literature on it, but I think is quite exciting, is the possibility of mediating long-term interactions with non-local classical communication. So by measuring something over here and by measuring something here, passing that data to a classical computer, you can actually sort of reconstruct what would have happened had you measured these together in a correlated way. All right. So that's a little bit on the overheads and sort of possible loopholes and alternatives, right? Other things we have to worry about in quantum error correction. So one interesting thing that you really have to worry about in quantum error correction is the fact that you're correcting errors with operations that are themselves faulty and prone to introducing errors, right? So in doing so, you have to make sure that you remove more errors than you're adding, right? You're doing more good than harm. So this intuition is captured in what's known as a threshold theorem, which basically says your baseline physical error rates need to be below some threshold, some cutoff, in order to be able to do more good than harm. So I don't know if I have enough time to talk to this plot, but basically, here's a plot for the surface code of different sizes. So here it's a 3x3 code, 5x5, 7x7, and so on. On the vertical axis is the logical error rate per error correction cycle. So I run one error correction cycle. How likely was I to have introduced a logical error? And on the horizontal axis is my probability of physical error after every physical operation, right? This is a log-log plot. So as I go left, I get better and better physical error rates. I hope to get better and better logical error rates and go down as well, right? So this diagonal dashed line I have on there is break even. So above here, you're actually doing more harm than good. Below here, you're actually correcting errors faster than you're introducing them. So that's one notion of the thresholds when you cross this one. There's another one about the vertical line. Ask me after the talk maybe, and I can tell you a little bit more about this. Cool, more, you have to also deal with faulty measurements. Maybe your measurement outcomes, you don't trust your syndrome. So what do? Maybe you repeat error correction a bunch of times. With the surface code, turns out you have to repeat it d times. So you're again picking up factors of 10, or with Google's distance 30 code, you're halfway to 100 on a log scale. And then finally, you have to worry about, again, propagation. So as you do your quantum computation, you have to make sure you don't take a single qubit error, like a bit flip over there on the far left, and propagate it to a larger weight error. So a bit flip followed by a gate that you maybe wanted to apply the C0 is equivalent to a 2-qubit error afterwards. And so you want to make sure you're not growing your errors uncontrollably. This introduces a notion of transversal gates, where you act on only 1 qubit at a time. And so it turns out that transversal gates, though, are incomplete. You can't do universal computation in a way that it's not guaranteed to propagate errors. And then out of the transversal, then if you write down your transversal gates, it turns out that they're not enough to, not only are they not enough to do universal computation, if you only have them, you actually get a circuit that's classically simulable, right? And so this leads to this whole field of study now of studying how do I do the non-transversal parts. The word here is called magic. You'll see a lot of people talking about magic state distillation, for instance, or how do you prepare and consume this resource that we just call magic in the field to do universal quantum computation. All right, I think I'll jump over this real quick. The idea is that there's a whole family of codes, full categories of codes that people look at. For each of these codes, you have to worry about sort of various things, like how do I find a better code, how do I find better decoders, how do I make sure that I can tolerate errors, that I'm not propagating errors uncontrollably, how do I do universal computation of these codes. But the exciting thing I want to tell you are maybe some recent breakthroughs in the field. So one very big one a few years ago that we're still sort of like still dealing with and absorbing in the field what its implications are, is the proof that good quantum codes exist. Right, so this is a very big deal, and it was an open question for a long time. So that was just 3 years ago that it was proven they exist in a few papers. I have to put an asterisk on that. Really, it was the proof that good quantum low-density parity-check codes exist, but really these are the only codes we care about, so you may as well say this is the proof that good quantum codes exist. There's a realization that it may be possible, through some of the loopholes I mentioned, to run these codes on local architectures. So that's a big, I have put some question marks there because we don't really know what the limits here are. And then I should note that while there's also been work on finding codes very recently, on finding codes that maybe aren't good in the technical sense, but seem to be better than the surface code in lots of ways. So IBM pioneered some codes that have now sent a whole lot of researchers studying these things called bivariate bicycle codes that are inspired by this, but it might be better than the surface code. All right, so I'd be remiss not to mention hardware demonstrations. There have been big breakthroughs of hardware demonstrations of error correction. So one of this comes from the Google, who showed her demonstration of a scalable architecture for error correction in superconducting qubits. Quantinuum also has some nice work showing logical operations that are better on the logical level than the physical gates they have. And then there's been some work on asymptotic reductions of the overheads of error correction. So either making these things either reducing the time overheads of error correction or the space overheads of error correction. There's been some work that I thought might have been the biggest paper of the year on improved distillation of magic states, until Google came out just last month with a paper that may make that obsolete. I apologize, but I appreciate that it did not, in fact, tell you a lot about what exactly magic states are, but they're used for universal computation with the surface code. And yeah, I'll just end with some thoughts on sort of the obvious and maybe speculative directions for error correction going forward. So first, there's more work to do on local codes like the surface code. So Google right now thinks that they're kind of maybe run into classical computing challenges. And so we want to build faster, better decoding algorithms and better ways to produce and consume magic states. There's a lot of work to do on non-local codes. This is now this big open field, especially with the discovery of good quantum codes. And then finally, there's a lot of, I think, in some ways this might be a little premature, but eventually we're going to have to think about how to organize quantum computations around the capabilities of error correcting codes, because we know this is a layer that you're going to have to go through. And usually algorithms people don't think about that too much, whereas we know in the classical world, some things you just do much better on a GPU than a CPU. Similarly, in the quantum world, sometimes maybe one error correction architecture might be a lot better suited for one algorithm than another. So that's worth thinking about. All right, thank you very much.